Yes. So, in the last class we saw that there are 7 crystal systems, and we associated both the single axis operation and also the operations which are more than one. Following the Euler's theorem, it has to be all 3 axes having rotation symmetry. So, we discussed those points, and then we said there are 7 crystal systems. Now, how do the shapes of these 7 crystal systems develop? So, here is something which I have written. Crystals use different shapes of regular box to build up into a crystal. This is a very interesting statement. That means that the different shapes of a regular box, you see the word regular means that it cannot have a dimension which is not available for the atom to occupy or the molecule to occupy. In other words, every atom has a certain volume and every molecule will have a molecular volume. And we know that by the definition given so far that we have to have close packing in a crystal. So, when these conditions are put in, the definition of a box, the shape of a box will have to be regular. We cannot have an irregular shaped box. So, therefore, we have to have 3 directions and 3 interaxial angles between these 3 directions, defining a regular box. And this regular box, there are 7 different ways in which we can develop them into crystals, because remember these boxes will have to follow the translational periodicity. So, if they have to follow the translational periodicity and still be regular boxes, in other words these boxes have to be packed in such a way that they repeat along A direction like that, B direction like that, and C directions like this. Imagine the situation where these boxes which are shown here, for example the box which is shown here for the triclinic system. So, the presence of the A direction here will repeat itself in the next unit cell, the next unit cell, and so on. B also will repeat itself like that, and C also will repeat in that particular direction. So, the repeat units A, B and C. So, if we now consider this as a unit A, this unit A now repeats in that direction, and so on. It forms eventually the crystal. If we consider this as the unit B, this B goes like that and like that and like that. So, it will extend and define our lattice, and so also the C direction. Right. So, if that is the way in which we want to have a unit cell, there are 7 different shapes, and these, remember these shapes come because of the nature of the rotation axis which we are using. So, in the case of the triclinic system, there is only one rotation axis, which is the one-fold rotation axis. That means it is a 360-degree rotation, and then the only other operation which can exist in a triclinic system is the center of symmetry operation, or the presence of an inversion center. The inversion center can be anywhere in this box. In fact, it can be anywhere in the 3-dimensional symmetry that is repeated by this box, and then we can always take an origin which is generally represented at this point in this diagram. So, that we have a defined value of A, a defined value of B, and a defined value of C. The angle between A and B is illustrated as gamma here. So, the as I mentioned earlier in the previous class, the angle between A and C will be beta, and the angle between B and C will be referred to as alpha. So, the conditions which define a triclinic regular box will be A not equal to B not equal to C, and alpha not equal to beta not equal to gamma, and also not equal to 90 degrees. If you wish, we can write that, because the values of alpha, beta, gamma are not equal to each other. Whenever these values are not equal to each other, the box length is A, B and C, which are again not equal to each other. We have a triclinic symmetry. So, if you identify somehow by some method which we are going to develop during the next series of lectures, somehow identify the method in which you can now see that the box, the unit cell which can be describing this particular crystalline product could only be triclinic, that means that there is no other symmetry that is present other than the possibility of the presence of an inversion center. So, other than the inversion center, there is no other symmetry that will be present except of course the 360-degree rotation axis, which is the one symmetry. The moment we bring in the aspect of a two-fold symmetry, things change rapidly. The shape of the box, in order to have the two-fold symmetry equivalence satisfied, that means the equivalent points now will be x, y, z. The equivalent points now will be x, y, z, and assuming that B is the unique axis, in this particular case B is shown as the unique axis. So, then it will be minus x, y minus z. So, in this particular unit cell, the equivalent points are x, y, z minus x, y minus z, and you see that the diagram which is now shown here is like a squished book. You take a book and then press it up like that, it will become a monoclinic system. The values now will be A naught equal to B naught equal to C, alpha and gamma are 90 degrees. So, the fact that we have a two-fold symmetry makes two angles 90 degrees with respect to each other. Whenever you have a two-fold symmetry, in whatever direction you have, in higher symmetry systems as we go further, we can have the two-fold symmetry in any other direction other than the A, B and C. In such situations, we can therefore find out the fact that whenever such a thing happens, the two-fold symmetry introduces two 90-degree angles across the direction of rotation. So, if the rotation axis is along B, we therefore get alpha and gamma as 90 degrees, beta will be non-90. So, this is the condition for a monoclinic system. Then this is the second regular box which we will have, which represents the symmetry therefore of 2. Along with 2, the other point groups which go as we saw in the previous class, 2 bar which is mirror, and also 2 by m which is a combination of proper and improper axis. So, these 3 point groups go with a monoclinic symmetry. With triclinic we have already seen it is 1 and 1 bar. In this particular case it is 2 by m and m. So, these 3 symmetry elements, these 3 point group symmetries are associated with monoclinic symmetry systems. So, a crystal forming a monoclinic, going into a crystal system monoclinic will always have the presence of either a two-fold axis or a mirror plane or a combination of a two-fold and a mirror plane. Anytime such a combination occurs and nothing else, no other symmetries are developing, the crystal system will uniquely be monoclinic. So, the definition of a unique triclinic and a unique monoclinic we have already seen. Now, we will go further to the third system, which is the orthorhombic system. In the case of the orthorhombic system, the values of A, B and C need not be equal. This is like a Bata shoe box. Well, I should not be saying Bata shoe, there are so many companies, but Bata is a company, but you are familiar with a Bata shoe box because most of you buy Bata shoes. I do not know why, but whenever you buy a shoe, okay, let us make it general. Whenever you buy a shoe, it is put in a box. I do not know why they do it, it is very flimsily made and we come home and throw it away, but it is put in a box and that box is given to you along with your shoe or chappals or whatever you buy. And that dimension is A not equal to B not equal to C. It so happens that there are 3 mutually perpendicular two-fold axes. Now, this is bringing back the Euler's theorem, because when we have a two-fold axis along, let us say A direction here and a two-fold axis along the B direction here, let me point out with a laser pointer. Suppose we have, this is the origin, this is the A direction and this is the B direction and that is the C direction. So, if we have this particular direction as the A direction, there is a two-fold axis here. The moment we have the two-fold axis, we told that if the two-fold axis is along the B direction, then 2 of the angles should be 90 degrees. So, if it is along the B direction, what are the 2 angles that have to be 90 degrees? In this particular case, the B axis was the unique axis, the 2 angles were alpha and gamma. So, if this is the A axis now, the 2 values will be beta and gamma. So, along the B direction we will have the alpha and gamma 90 degrees, along the C direction we have the other 2 angles 90 degrees, and therefore, we get a condition A not equal to B not equal to C and alpha beta gamma are 90 degrees. So, this is another regular box which is representing a unit cell. So, crystals which go into this will have to obey all the 3 two-fold axis symmetries which are operating on them. So, every point in this box now will have a 2-2-2 symmetry, a 2 symmetry, or 2 by m, 2 by m, 2 by m, which is referred to as m symmetry. And these 3 therefore will refer to the point groups, 3 different point groups. So, we have 1 and 1 bar here, 2 m and 2 by m here, and 2, 2, 2, 2 and 2 by m, 2 by m, 2 by m, which is represented as m. So, we therefore have covered 3 plus 3 plus 2, 7 point group symmetries by going from triclinic to orthorhombic. Well, as we go to the next slide, I will show you the remaining part of the unit cell. Of the 7, we have 3 of them covered. We will have 4 more to cover, and these 4 more are the tetragonal, the cubic, the hexagonal, and there is a very special system which is referred to as the rhombohedral. So, we therefore have a total of 7 crystal systems. In the tetragonal symmetry, we will have the presence of a 4-fold rotation. So, the tetragonal symmetry can have a simple single 4-fold rotation. The 4-fold rotation will ensure that if certain conditions on the type of the regular box we can have. It is like a column or a pillar. The base will be a square, so A is equal to B, and then this particular direction, the third direction about which we have the 4-fold symmetry, need not be equal to A and B. So, the presence of the 4-fold symmetry therefore introduces the concept that A should be equal to B. So, whenever you have a square lattice, we have already seen that whenever we have a square lattice, the square lattice will effectively introduce A to be equal to B, and it is not equal to C in this direction, and alpha, beta, gamma are 90 degrees with respect to each other. So, this can also be treated as a stretched cube, and this essentially you take a cube and stretch it in a direction perpendicular to the base plane, then you will get a stretched cube. This now defines a tetragonal system, and in the case of a cubic system, now what we do is we compress this system and we get to A, B, C, alpha, beta, gamma, A equal to B equal to C, A equals B equals C, alpha, beta, gamma are 90 degrees, a very symmetric isometric system in fact. These are also referred to as isometric crystal systems. So, in the case of a tetragonal symmetry, what are the point groups we get? We get the point group definitely 4. Now, other than the point group symmetry 4, what other point groups we can get? So, we will now study the point groups in full detail as we go further in the next few classes, so that you are now getting ready to do all the assignments which will come in your way. You can anticipate the assignments. The assignments will be that given a tetragonal system, what are all the point groups which you can associate the tetragonal system with. For example, 4-fold symmetry, a mirror perpendicular to the 4-fold symmetry which gives you 4 by m, and then the operation 4 by m, 2 by m, 2 by m, and also the operation 4 to 2 which is allowed, and things like that. So, there is a large number of point group symmetries that will get associated with the tetragonal system. Remember that we have only a total of 32. So, we have to take the 32 point group symmetries, distribute it among the individual crystal systems. So, what we have done is we have given it 2 to triclinic, 3 to monoclinic, 3 to orthorhombic, and several of them to tetragonal and so on. When we come to the hexagonal system, to extend this discussion, instead of the C axis having a 4-fold symmetry, the C axis can be associated with a 6-fold symmetry. Since this is a 6-fold rotation axis, we should have a 120 degree angle, and therefore gamma now is 120. Alpha and beta have to be 90 degrees in order to have the 6-fold rotation axis coming perpendicular to that, and therefore we have a condition A equals B not equal to C, alpha beta 90 degrees and gamma 120 degrees. So, this defines now a hexagonal system. A special case of a hexagonal system gives rise to the so called rhombohedral system, where we essentially have a hexagonal system, but then this hexagonal system is very special. It becomes in such a way that A is equal to B equals C, alpha beta gamma are all equal to each other. The difference between the rhombohedral system and the cubic system is the fact that this angle is not equal to 90 degrees. The moment it becomes all 3 equal to 90 degrees, we will have a cubic system. and therefore effectively we have 7 crystal systems, and these 7 crystal systems are associated with the type of rotation axis which we can give to them. The type of rotation axis we can give here is a 3-fold rotation axis, but that is a very special direction in the case of a rhombohedral symmetry. Same is true with the cubic symmetry. We give the 3-fold rotation axis along the diagonal, and then only we can define a cube. So some of these features are right now obscure and a little bit confusing as we keep discussing, but therefore what we will do now is to go away from this 3-dimensional thinking process, because we already said that 3-dimensional thinking has not been with us since we went to school, because we made the basic mistake of joining school and losing the 3-dimensional thinking and went down to 2 dimensions. We will now examine the possibility of 2-dimensional symmetry, and that brings us to a very interesting discussion on what kind of plane lattices we can think of in 2 dimensions. So these are therefore the 7 crystal systems: the triclinic, the monoclinic, the orthorhombic, and so on, tetragonal, cubic, etc. I am repeating it just to drive home the point of the types of point group symmetries which you can distribute to these 7 boxes. So we have 7 crystal systems and 32 point groups and nothing else. The nothing else issue comes up mainly because we have translational periodicity. If translational periodicity was not there, then things would have been very different, because the translational periodicity has put restrictions on the types of rotation axis we have 1, 2, 3, 4 and 6. And because of that, and also because of the fact that we have periodicity in A, B and C directions in these boxes, we have only 7 types of boxes. And remember that the 3-dimensional space which is generated by any of these boxes will have to have that particular symmetry. In other words, if there is a triclinic symmetry, triclinic crystal, and it has only 1-fold rotation, then all the points in that particular unit cell will have 1-fold operation. Any point x, y, z will undergo 1-fold rotation. On the other hand, if there is a associated center of symmetry or inversion center with respect to the triclinic system, then the associated symmetry system will also have to be present in every point in that 3-dimensional box. Suppose we have a tetragonal system, for example, every point in this unit cell and also the entire lattice which we can generate by translational periodicity operation will have the 4-fold symmetry. It must have the 4-fold symmetry. So the presence of the 4-fold symmetry ensures it is a tetragonal system. The presence of the 6-fold symmetry ensures it is a hexagonal system, and so on. So these definitions therefore now make a solid material study become more and more systematic. So if materials crystallize in these systems, it does not matter if a molecule, we saw the molecular symmetries in the previous class. So if the molecular symmetry is 5-fold symmetry, it does not matter as long as it can be fitted into any one of these 7 boxes with the symmetry obeying the symmetry rules which are put on the box and on the system. It is not necessary that the molecules should have the same symmetry that is associated with the crystal system. So the molecular symmetry and the crystal symmetry can be very different. However, Kitagorowski had demonstrated that if the molecular symmetry has a presence of an inversion center, for example, that inversion center will be utilized in the unit cell associated with that particular compound. So suppose there is a compound with an organic compound or an inorganic compound which crystallizes with the presence of a inversion center at its center. That center will now coincide with the center of inversion associated with the crystal system. So the crystal system therefore invokes the possibility of occupation of these molecules at the special positions. So the special positions will occur, in other words, on situations where we have the presence of the molecular symmetry. The occupancy of the special positions are invariably done only when the molecule has the similar symmetry. And this is a point which we will have to keep in mind when we study crystal structures. So if we have a knowledge of what molecule it is, and if we have a knowledge that that particular molecule has 1 bar symmetry, then if it goes into, let us say, a triclinic system, then we know it has to be P1 bar. Just to extend this argument, if in case we have only an L amino acid, because L amino acids form a protein. So, if you have a protein which crystallizes in a triclinic system, it cannot crystallize in P1 bar, it has to crystallize in a P1 system. So, in other words, the protein crystals with naturally occurring amino acids being present in a protein, or for that matter peptide units which have all L units or D units, whichever way, if we have synthesized, these kind of molecules will not go into systems which have a center of inversion. They have to go to non-center symmetric space groups. So, when we discuss about how these systems go into different kinds of groups, space groups, and eventually crystal systems, we will bring in the restrictions which come as a consequence of this. That we will do later. So, what we thought was we will now look at, as we mentioned again, that our understanding in twofold objects is much easier, the two dimensional objects is much easier, and therefore, we will look at two dimensional plane lattices. It is we can demonstrate that there are 5 two dimensional lattices or 5 plane lattices. The first lattice by definition of it, we have already seen the definition of a triclinic system, is made from A. The value of A here is not equal to the value of B. So, if we now call this as A and this as B, and this is the angle gamma, then we see that A is not equal to B and gamma is not 90 degrees. So, this defines the so called oblique P lattice. What is very interesting is this oblique P lattice has the lattice points at the unit cell edges. The lattice points at the unit cell edges will now have, because it is a plane lattice, there is no third dimension. So, because there is no third dimension, the symmetry that is associated with this point will be a twofold. So, the minimum symmetry associated with an oblique P lattice is a twofold symmetry, and this twofold symmetry has will repeat itself at all these 4 corners wherever there are lattice points. In addition, because it has a twofold symmetry, the presence of other twofold symmetries halfway between A direction, B direction, and also along the diagonal will automatically appear, and that is because of the fact that we have x, y, z, in this particular case x, y, 2 dimensions, x and y be representing A and B. So, if there is a point x, y here, this particular point will see the twofold axis up there. So, it will undergo a twofold rotation and go to that point, and this now when translated by 1 unit will come down here, because of the lattice periodicity we can translate it by 1 unit, and this now again translates into 1 unit and comes over here. That means the object which was here will also generate an equivalent point there, and because these two equivalent points are related by this twofold axis, the presence of the central twofold axis becomes invoked, and therefore, the presence of twofold axis at these points, symmetry at these points, the presence of the twofold symmetry introduces twofold symmetries at half along A, half along B, half along A and B, and therefore, we have there the presence of additional twofold symmetries. This happens not only in 2 dimensions, it will also happen in the 3-dimensional unit cells. Whenever you associate a symmetry with a lattice point, that symmetry, the same symmetry more often than not, unless otherwise specified, when we go to higher symmetries we will have more issues coming up, but in most of the cases whatever symmetry is put at these origin, 1 unit translation in this direction, 1 unit translation in that direction, 1 unit in this direction, 1 unit in that direction, automatically generates the same symmetry at halfway points, and therefore, we get the twofold symmetries at these half points. This is a criterion which we have to considerably worry about, because when we have objects which have symmetry associated with an oblique P lattice, it will invariably possess this feature. So, an atom which is up here will have to appear at this point, and these two now define the two equivalent points associated with the oblique P lattice. Very often than not, we think that oblique P lattice has a third direction, but we are considering only the plane lattice, and the third direction is undefined. Such symmetries will occur in what we call as liquid crystalline objects. In liquid crystalline objects, the plane symmetry only remains. The lattices are forming twofold symmetries, but the third symmetry is undefined, or it will have a certain property which is not a periodic in nature. So, the periodicity in the third direction may not be present. In such situations, it is good to know to represent the two-dimensional periodicity in this fashion, and that is how the 5 plane lattices are very crucial to understand fully. So, having seen this, that the fact that the oblique P lattice now will generate 2 equivalent points, and then all these symmetry positions, these are the symmetry axis coming up at various positions. This is therefore the property of the two-dimensional oblique lattice. Now, what happens in case we have a line of symmetry? Because we do not now have to have a situation where we have an axis of symmetry, where we have to have a plane of symmetry, because if we have to have a plane of symmetry, that plane of symmetry will not define a plane lattice. So, whatever we consider as a plane now can be considered as a line lattice. So, we have therefore the line axis, so the line of symmetry. So, this is a periodic repetition in 1 dimensions. This is a 1-dimensional lattice which has a line symmetry. So, this line symmetry now is represented by these points which are now repeated at, let us say, A. So, this is a 1-dimensional lattice. Now, the 1-dimensional lattice may have a point which is associated with the line of symmetry, or it can also have a point which is midway between the lines of symmetry. So, there are 2 possibilities. Only in this particular case you have the line of symmetry. The point which we are associating could be on the line of symmetry or halfway to the lines of symmetry, and because of the fact that these we have either on this or that, it opens up 2 possibilities. One possibility is a 2-dimensional lattice which we can generate as indicated in this figure C, which now tells you that this is the 2-dimensional lattice, and that is a 2-dimensional primitive lattice which is now a rectangle. As you can see that this represents a rectangle because this distance is different from that distance. So, we have a situation where we get this primitive lattice, and that is indicated this way. So, if you have this value as A and this value as B, this is the gamma value. So, what happens therefore to gamma? Gamma becomes 90 degrees. Gamma becomes 90 degrees, and therefore, we have A not equal to B and gamma is 90 degrees. This now represents a primitive rectangular lattice, rectangular P lattice. Notice that when we want to say primitive, that means the total number of, that is very important, we have not defined it yet. I think it is time to define what is meant by a primitive lattice. A primitive lattice is one in which when we take all the lattice points in the unit cell, like for example 1 translation, 1 translation, 1 translation, it again repeats itself in all 3 directions. So, you take the oblique P lattice. In the oblique P lattice we have points which will be coming at these 4 positions. If you take the next 4, it will come there, the next 4 will come there, the next 4 will come there, and so on, and therefore, every point therefore is shared by 4 unit cells. In the plane, every point is shared by 4 unit cells, 1 unit cell here, 1 unit cell there, 1 unit cell there, 1 unit cell there with respect to this fellow, and therefore, the occupancy of this will be 1/4, and therefore, if you add all the lattice points in the unit cell, you get 1/4 plus 1/4 plus 1/4 plus 1/4, you will get a total of 1. So, in any primitive lattice, the number of lattice points will be 1. Okay. This is a point which we must notice, and so in this particular case, in the case of the rectangular primitive lattice, again the number of lattice points turns out to be 1. You can see it here. This is the unit cell, you take this as the unit cell. This point is shared by this unit cell, that unit cell, this unit cell, and that unit cell, and therefore, you get the lattice point value here is 1/4, and therefore, this particular unit cell will have a total of 1, and this repeats itself in all 2 directions, generating the so called 2D lattice, in which the property of the line of symmetry remains. That means we have this line of symmetry, that line of symmetry, and at this this is along the A direction. Along the B direction we will have a line of symmetry there and a line of symmetry there, and just the way in which we defined the earlier case, the two-fold axis of course has to be there in this particular case. So, the two-fold axis is already located at these positions, and the line of symmetry will also repeat, as we mentioned that if we have a symmetry element at the point 0 0 0 and one translation that is of the same symmetry element, the corresponding symmetry element will repeat halfway distance. So, therefore, you get this kind of a grid which now represents the rectangular P lattice. So, any point in this particular position we will see not only the two-fold axis, it will also see the line of symmetry about which it can move around, and this A equals B and the angle gamma therefore will represent the so called rectangular P lattice. So, this is one way of representing the rectangular P lattice. This is another way of representing the rectangular P lattice, where we have the points in the middle, but we still have the rectangular P lattice, and therefore, we have the symmetry that is identified with respect to the primitive lattice. I think we will stop here for today's class.